Okay, we're still finding antiderivative here, but it's just the notation can look a little, there's different variations of notation, so just want to point that out. So we're going to talk about differential equations a lot more next unit, but really differential equation just means that it's an equation that involves derivative. So if something is in the form of y prime equals whatever, or dy dx equals, that's a differential equation. There's a derivative and there's the equal sign. Call that, yeah, that's a differential equation. So when we talk about solving a differential equation, that just means that I want to get the derivative up to the function level, and that just means take the antiderivative. That's all it means. Okay. Steps for different equations. We're going to rewrite y prime as dy dx. Separate variables on either side of the equation. Take the integral of both sides. So right now we're really just working on the right side. Next unit, we're going to work on both sides of the equation. That makes it a little bit more involved, but really left side, you're just going to represent left side as a notation. Okay. And then we're going to solve for C after finding a specific solution to the differential equation. So remember we talked about how we need a plus C if we want to represent a family of functions that all share the same derivative. But if we have enough information given to us in the problem, we're able to actually solve for C and find the specific scenario for that particular function. So let me just walk through a couple of examples with you. Okay, so number 3, suppose y prime equals 2 and solve for y. So we know y prime is the same thing as dy dx, but it's just helpful to write it as dy dx. It's more visually more informative. It has more, it just gives us more information for us to set up. So I prefer that. So y prime equals 2 is the same thing as dy dx is equal to 2. And if I want to solve for y, first we're going to separate the variables. We're simply going to gather the y's on the left and everything else on the right side. So if I multiply that dx over to the right side, or cross multiply, I'm left with dy is equal to 2 dx. Left side, we're going to take the antiderivative with respect to y. The right side, we'll take the antiderivative with respect to x. So imagine that there's what number is hidden in front of this dy? There's a 1, right? So I'm going to take the integral of 1 dy and integral of 2 dx. So what do you think 1 dy will turn into? Just what? Just y. Okay, so that dy tells us this side is with respect to y. So 1 is y to the 0 power, and I'm going to make that y rise up to the first power. So it's just equal to y. And then the right side, what do you think integral 2 dx becomes? 2x. Yeah, so the 2 is going to hang out in front, but yes, that dx rise up to that degree 0 rises up to degree 1. We have a x. Now, technically, both sides produce a plus c, but we're just going to gather all the c's together and just write it once on the right side. Oh, sorry, my bad. Thank you. 2x. Now, all the ones that we see right now are all going to look like this, where you're not going to do much on the left side. It's always going to be 1 dy, and it's always going to turn to y. It's just the right side that we're going to do work. Okay, so we call this a general solution because there's still a c left over. We're on page 32.
Do that.
No. I just wanted to show you that when I ask you for a general solution, you're going to leave that plus c there.
Do you always add plus c to the right?
Yes, just always add plus c to the right. Yeah, good. Okay, example 4, we're going to find, again, the general differential equation. So again, I'm going to cross multiply here, get the x's on the right and then the y is on the left. So dy is equal to x cubed dx. There's a 1 hidden in front. Take the integral. All right, so again, 1 dy becomes just y, yeah. On the right side, this is set up nice and ready for power rule. X cubed becomes what? Yeah. X to the 4th over 4, right? So with power rule for antiderivative, instead of multiplying and subtracting 1, we're going to add 1 and divide by that number. Plus what? Plus c. It's asking for a general equation, so that's what we're able to provide. We're done there. Now, example 5 says solve the specific differential equation. So that means that a plus c is going to show up initially. We're always going to get to the general equation first. And then the specific just means take the necessary information, or take the information that they give you and see if you can convert it to find that c value, find a numeric value for c. Okay. But even if they ask you for a specific, you're always going to go through general first. Okay, you're always going to get that plus c to show up before you do anything with it. So general means plus c shows up. Specific means find what that c value is and replace that c with a number. Okay, so y prime equals 3x minus 4. Let's get that dy dx to show up. I want to find the derivative of y with respect to x. What would your next step be? Yeah, let's move that dx over to the right side. Yep. Okay. X is on the right. Take the integral of both sides. Right now, we're not going to do much on the left side. It's always going to be 1 dy, so it'll turn into y. Right side, we have 2 terms. Both terms are set up and ready for power rule. No cleanup needed. 3x becomes 4 becomes 4x. And don't forget a plus what? Plus c. Okay, so we have the general. Now we're going to go one step further because they're asking for the specific. So specific just means what can we do to find the specific c value. So now they have a very specific point on the curve, so we're able to pinpoint exactly where this equation is. We're no longer having to represent a family of functions. We can pinpoint the specific graph that goes through this point. So the way you do this is you take your 4 and your 10, replace your x and y, and solve for c. And once you have c solved, then you can replace c with a number, and we can call this the specific solution. Okay, so we're going to plug in 10 in for y and 4 in for x. Okay, this is 16. 16 divided by 2 is 8. 8 times 3 is 24. Subtract everything over to the left side here. Let's see, 24 minus 16 is 8. 10 minus 8 is 2. So c is equal to 2. Now, once you solve for c, make sure that you don't just stop there because we have to, our goal is to update this equation, right? So it's asking for a specific differential equation or solve this differential equation. We're trying to find a specific solution. So now we have y is equal to 3 halves x squared minus 4x plus 2.
Did you get 2 again?
Oh, right. How do we get 2 again? So we took the order pair 410. We inserted into the x and y of the general equation, isolated c, and once we solve for c, we replace the c back into the general equation. Okay. Any other questions? Okay, let's do one where it's a little bit more involved in the sense that we need to go up 2 levels. So let's say we're starting at the second derivative level, and we're trying to make our way up to the derivative level and then up to the function level. So we got to do solve the go through the process twice. So remember, last semester we were able to go from f to f prime to f double prime. And this semester, we can move from f double prime up to f prime up to f of x. So instead of taking the derivative twice, now we'll take the antiderivative twice. We'll do antiderivative power rule twice to move up the chain. But as we go through that process, each time we go through the antiderivative process, we're going to get a plus c each time we take the antiderivative.
That's how you get the number of terms back.
I'm sorry?
That's how you get the number of terms back to where.
Right, yeah. So that's a good point. When you find the derivative, you keep losing terms, but when you take the antiderivative, you're going to keep adding your terms back. Yeah. All right, so it says suppose f double prime is equal to 6x plus 4, f prime of 0 equals 3, f of 1 equals 5. So we have an order pair at the first derivative level. We have an order pair at the function level, and that's helping us to find each of the c values along the way. So we're starting with f double prime. So I'm going to say f double prime is equal to 6x plus 4. Okay. If I want to find f prime, I got to take the what of the right side, not derivative, antiderivative. Yeah, we're at the lowest derivative level. We're trying to move back up, so we got to take the antiderivative of 6x plus 4. Okay, we're going to resolve this, and once we clean it up, we can call that the f prime. This just tells us the action that we need to do in order to get this up to the f prime level. Okay, so 6x becomes plus 4x plus c. Now, I'm expecting that there's going to be another c value that shows up with the next antiderivative I take. So I just want to kind of indicate that there's a distinction between them called the first, the c sub 1. Now up here I said plus c and plus k. You can use that as well, but I'm going to use c sub 1 for the first one and c sub 2 for the second. It just feels like that plus k can feel a little strange using different variables. So, okay.
Can you convert the 6 over to 3?
Yeah, that's right. So good. Yeah, we're gonna do a little bit of cleanup before we try to solve for c. Thanks. Okay, do we have an order pair at the derivative level that we can use? Which is what? Yeah, so we'll plug in 0 in for x and 3 in for f prime of x. Okay, so this is the y value of the f prime. So 3 will go in to this slot and 0 will go in for the x slot. Right, nice and clean, right? C is equal to what? Or c sub 1 is equal to what? 3. Okay, so let's update the f prime. Get it up to the specific f prime, and then we can take the next step up to f of x. So here's my f prime all cleaned up. Okay, so we're halfway there. Any questions so far? Okay, so we're going to go another antiderivative up, right? So I want to get from f prime to f of x. To get from f prime to f of x, I got to do what of this expression? Yeah, integral antiderivative. Yeah. So once we perform this action, the result will be at the function level. Okay, 3x squared becomes 4 becomes good. And then the 3 becomes 3x. Yep, every degree is going to rise by 1, even the constant. The constant is going to rise up to 1. And then there's another one that shows up, plus c. I'm going to call it c sub 2. Yeah, because this is the second one that shows up. I'll do some cleanup, and then I can use my order pair at the function level to help me get to my new c value. So I have an order pair at the function level, plug 1 in for x, plug 5 in for y, and that can help me isolate c sub 2. Once I solve for c sub 2, then I can update this and convert this from a general to a specific. Right, well, this specific is only halfway. We need this specific to get to this specific. So really, the answer I'm looking for is the specific of just f of x. That's a good question. Why is there an order that does it matter which c we use for each of these? It does. Because this is at the f prime level, we can't plug the 0, 3 into this function because it's not at the same level. Right. So yeah, so the notation is going to tell us which one is appropriate. All right, good. All right, so 5 is equal to, so replace every x with 1. Clean all that up. 1 plus 2 is 3. 3 plus 3 is 6. 5 minus 6 is -1. So now I'm just going to rewrite my function f of x and replace c sub 2 with -1, and that's my final step. Okay, questions? All right, let me show you one other variation. This one is going to look a little different because we have g double prime. We're trying to make our way up to g of x. We're trying to find the specific solution, but both our order pairs are at the function level. So that feels a little strange, but we'll just see how far we can get knowing what we know. Okay, so we're at the second derivative level. We're going to move up to g prime. So I'm going to indicate where I'm headed. I want to get to g prime. To get to g prime, I need to do what with this expression? Antiderivative integral, yeah. Okay, g prime equals 12x becomes 6 becomes plus c sub 1, right? We know that we're expecting to do this twice, so I'm going to go ahead and identify that as c sub 1. Okay, let's do some cleanup here. G prime equals okay, do we have enough information to solve for c sub 1? Why not?
Like,
Okay. That there's no order pair at the derivative level. Okay, so we're forced to have to hold on to that C sub 1 as we take another antiderivative. Okay, so just treat C sub 1, pretend like that's a 1 or 3 or 5, but it's just we have to hold on to that this notation. Okay, so this is as far as we can go at the G prime level. We're going to go ahead and move up to the G of X level. So I'm going to set up what I want to do. I want to take the integral again. I can do this even though I don't have this quite resolved yet, because I just don't have enough information to do anything with it except keep it. Okay, so I'm going to take the integral of this expression, and after I take this action, this will move me up to the G of X level, but I need to do this action to get it to where I want to be. Okay, 6x squared becomes 6x cubed over 3. 6x becomes okay, this is interesting here. What do you think C sub 1 will turn into? Good, C sub 1x. Pretend that's just a number, right? Before any number from the F prime level, we'll just move up to a degree 1. So we'll do the same thing here. So plus C sub 1x. But this will produce its own what? Yeah, its own C sub 2. So a C sub 1 and C sub 2 will show up because before C sub 1 was just a constant, but now it's a degree 1, but then there's another constant that will show up again, right? Yes.
So you said we could use C and K instead of C.
Yeah,
And
you
it's
can.
like the same thing.
That's fine. Yeah.
Okay.
Yeah, you can use K for the second one if you want. You can use C and K. You can use C sub 1, C sub 2. Those are the most common variations, so it's up to you. I'm going to use C sub 1, C sub 2. Let's do some cleanup, and then let's talk about, is there a way to get to both of the C values, even though we didn't solve it at the G prime level? Now, we have two order pairs, but that's good, right? The whole purpose is that we need two order pairs to help us solve for 1C at a time. Which one do you think could be more useful as a starting point? Yeah. Why is that 0, 4 preferred as a starting point? Good. So 0 will take out one of the C's, which will isolate the other one. I mean, it forces us to solve for the other one first, but it doesn't really matter, right? It doesn't matter. We don't have to solve for C1 before we solve for C2. We just have to solve for each of them eventually. So we're going to go after the one that feels easier. Anything with a 0 will take out a lot of terms for us. Okay, so we'll replace 4 in for y and 0 in for x. That's good. All this wipes out. C sub 2 equals what? Okay, so I'm going to update this equation with my value that I know for C sub 2, and then I can use this order pair 1, negative 2 to help me get the rest of the way to solve for C sub 1. So I will replace 1 in for x, negative 2 in for y, and then I can get that final step that I need to solve for the other C. Two plus 3 plus 4, that's 9. Subtract 9 from both sides, I get negative 11. So now I'm able to get down to that final step here. Replace C sub 1 with negative 11. 7. Sorry, yeah, it's 9. So there's a 4 here.
Oh,
4 plus 3 plus 2, yeah. Yes. They are. They're both at the same level. They're both at the g of x level. So the first one is g of 0 equals 4. The second one is g of 1 equals -2. Well, the only thing is we couldn't find c sub 1 at the g prime level. But once we got both the C1 and C2 up to the function level, then these are at the same level now. We can use both. Yeah. It's just that, yeah, we couldn't solve for C sub 1 earlier because we did not have data at the G prime level to help us solve for that. Hold on, let me write this first and then again. G of x equals. Yeah, question.
Can you do like both of them at the same time? Like the G of 0 and the G of 1. I did like the G of 1 before the other one by accident.
Mm-hmm.
And I got like 12. And I got -12, not -11. Like, I don't know.
Okay, yeah, let me
Because I got like C1 plus C2 equals -8 somehow. But then I found out that C2 is 4.
yeah, if you plug in 1, -2 first, you'll have both C1 and C2 unresolved.
Mhm.
And we could go through systems of equations to help us solve, but I think we can do it that way as well. But the easier path is going to be taking advantage of the 0. But I can look at your work afterwards. Okay, but that's doable too. We should be able to do that as well, but that will probably take a little bit longer. Yes.
I didn't know if you're solving for C2 versus C1.
We just know we have to solve for both of them.
So it doesn't matter the order.
It doesn't matter the order. It just so happens that because we want to take advantage of 0, this just happened to take out C sub 1 and we're solving for C sub 2 first. We're just kind of going down the path of least resistance, and that's what it took us to.
So the answer would be, did the 4 and the 11 switch slots in?
No, it can't. Yeah, if we're solving for C sub 2, that's the constant, and that needs to stay here. We can't swap. If we swap those points, then it'll no longer be the same function. It will no longer fulfill the conditions. Yeah.
So we always be able to solve for all C values no matter what. Like
Yeah.
always be able to.
Unless I don't give you order pairs and I just ask you for a general equation. If I ask you for a general equation, then you would get to this point and you would stop. It is, well, I'm going to let you use the calculator for the entire quiz, but some parts like this, you have to show your steps. Other parts, you can use your calculator to check all your answers, but some parts I'll be looking for specific. I'm looking for your steps. Yeah. Okay. All right. One last thing here before we do quiz review is we're going back to Riemann sums, but we're doing Riemann sums from the perspective of how AP exam likes to present informations to help you so that you can grab data for your rectangles. Okay, so we're on page 35. Okay, so it says select values of a function are given. Part A says give the middle approximation with 3 subintervals on the interval from 0 to 20. Now, I want to make sure that we understand middle approximation doesn't mean midpoint. It just means whatever data is in the middle of your order pairs. Okay, so not necessarily the same thing as midpoint, not necessarily, or I'll say not midpoint. A lot of times it's not going to be midpoint, right? But there's a very specific way that they're going to ask you to get the data for a middle approximation versus a left-handed rectangle versus a right-handed rectangle. Okay, so we're talking about rectangles here. What's the area formula for a rectangle again? Okay, I'm going to use width and height. Okay. Now, to get the width information, that's going to come from your first row. To get the height information, That's going to come from your f of x. But we're going to pull the width and height in different ways, okay, in different ways. We want to first break down into 3 subintervals. We're going from 0 to 20. So not every subinterval have to be the same width. They just have to have the same number of order pairs. So if you look, I have 3 here, 3 here, and 3 here. And I'm going to be doing overlaps. Okay, so every subinterval will overlap with the next subinterval. So I want us to do this here. From 0 to 8 is one subinterval. From 8 to 12 is a second subinterval. And from 12 to 20 is the third subinterval. Every subinterval, make sure you start at the center of your order pair and move to the center of your final order pair. Don't start at the ends. That will mess up your ability to calculate. Now, these are not the same width, but they all span the same number of order pairs. You see how this one goes across 3 order pairs. This one goes across 3 order pairs. This one goes across 3 order pairs. The first row is the x value. The second row is the y value. Are we good so far? All right. Now, to get the width, we're going to have to count the distance between these endpoints. So we're going to subtract. What's 8 minus 0? 8. That's the width of my first rectangle. What's 12 minus 8? 4. That's the width of your second rectangle. What's 20 minus 12? That's the width of your third rectangle. You're not going to add these numbers together. You're going to subtract, okay? Because you're going from 0 to 8, that's 8. From 8 to 12, that's not 20, right? To go from 8 to 12, that's only a distance of 4 units. Now, for the second row, you're just simply going to pull the y value depending on where it's located. So every subinterval here has 3 y values. The 4 would be for the left height. The 3 would be for the right height, for the height on the right. And the 2 would be the height in the middle, because 2 is the y value that lands between 0 and 8. It's not directly between, but it's what we can use. And you're never going to have to find the average of any numbers. You're just always going to take whatever they give you. So this could be up at 7, and 7, 2 would still be the one that we use. Okay, so we don't want to overthink it. We're not going to have to do a whole lot of calculations here. You're just going to pick out whatever they give you. So go ahead and circle those numbers. So every rectangle will be width times height. Okay? So first rectangle is 8 times 2. Second rectangle is 4 times 7. Third rectangle is 8 times 6. So give the middle approximation. We do 8 times 2 plus 4 times 7. Okay, you can use your calculator for this. I get 92.
You put like units or anything that you.
Not unless the problem asks you for it. No. So I think this is an easy process, but I feel like I think it's good if we go through the first page and then have you guys try the second page, and that way I can kind of walk around and see if there's any issues that you guys are experiencing. We can correct it, and you don't have to, and so that it doesn't snowball into where you're missing a whole bunch of problems because you misunderstood something. Yeah. I'm sorry.
Would always be the same number of values on the table. It like change.
You mean like here? There's 9 order pairs.
Yeah.
There could be more. Sometimes I might be asking for 3 rectangles. Sometimes asking for 2 rectangles. But every interval that you draw, you're always going to have the same number of order pairs. They may be different widths, but they all span across the same number of order pairs.
Subinterval like 1 rectangle.
That's right. Each subinterval is 1 rectangle. Good. Yeah. Each subinterval is one rectangle. Okay. Let's look at part B. Use right-handed rectangles to approximate with 3 subintervals from 0 to 20. Okay, so this one, we're also spanning from one end to the other end. And again, it's 3 subintervals, so it looks like it's going to be the same width across. So every time you draw your subinterval, make sure you start in the middle of your order pair and end at the middle. And also the second subinterval will overlap the previous one. So again, width of 8, width of 4, and width of 8. You're just subtracting your x values. 8 minus 0, 12 minus 8, 20 minus 12. Now it's asking for a right-handed rectangle, so how is that going to impact how we grab the y value? The one on the right, yep. So the first rectangle will have a height of what? 3. Second rectangle, height of. Third rectangle, height of 10. Yeah. Okay, part C, use 3 left-handed rectangles to approximate area 3 subintervals on the interval from 0 to 9. What's different about this one? Say it again? Yeah, so we gotta be careful, right? So here, we're only going from 0 to 9, so we can't just make sure you pay attention to where you're starting and where you're ending. We can't assume that we're using the entire table, right? So in this case, if I want to go from 0 to 9, every subinterval only span across what? 2. So 0 to 5, 5 to 8, 8 to 9. Now, if it spans across 2, I'm never going to ask you for midpoint, okay? Because I'm never going to ask you to find the average between two numbers. If I ask you for, sorry, not midpoint, if I ask you for middle rectangle, you're always going to have a physical middle order pair to pick from. Okay? So if you see a span like this, the problem will never ask you to do middle rectangle because there's only left and right available. So you don't have to create your own order pair. It'll always be there for you. Okay? So the width of my first rectangle is 5. Second rectangle, 3. Third rectangle, 1. Left-handed rectangle. So my first rectangle will have a height of what? Then 2, 3. Okay. Okay, last one here, trapezoids. Trapezoids has a distinct formula. It's not width times height. However, we are still going to use width and height, but the area of a trapezoid is 1/2 width, height 1 plus height 2. Every trapezoid, we're going to have to include 2 heights, and we're not going to subtract it. We're going to add the heights together. Okay. Now, how many trapezoids do we want here? 2. Spans from 0 to 20. So every subinterval will see the same number of order pairs. So we want each to have 4, right? So sometimes you have to kind of look and count before you commit to it here. But here I go from 0 to 9 and then from 9 to 20. First trapezoid is width of what? Second trapezoid, width of 11. Now, what heights am I going to use for my first trapezoid? What do you think my height 1 and height 2 is? 7 and 4. Good. The most common mistake that I see, students want to subtract the 4 and 7 because that's what they did with the width, but you're not going to do that. You're going to add. The second mistake that I see is some students, they feel like, oh, I got to use all these heights. So they do 4 plus 2 plus 3 plus 7 for the first trapezoid, but that's not the trapezoid formula, right? We only use the ones that the ends touch. And then careless mistakes that I see students make where they would pull the heights from the x value, or they would pull the width from the y value, and then so yeah, it's not hard, but it's also easy for students to to make a mistake just because they misread something or so. I'm hoping that if we practice enough, that these should feel like gimme points, right? So that's the hope. Okay, we have a little bit of time here. Can we try the next page here? Page 36. And I want to walk around and see how we do with this. So spend like maybe 4 minutes, see how much you can do. On just see if this really is you're getting it as well as I would like to get. So yeah, it's fine. Okay. All right, I'm marking it. Yeah. Question. Yeah, still rectangle. Yeah, yeah. So anytime you see, I know sometimes it doesn't mention rectangles, but we're going to assume that's always rectangles unless they say trapezoids. Oh yeah, one just means that we're starting at one and we're ending at one. Yeah, this just means that we're starting at 0. Okay, I'll say that. Let's look at the x value. Got it. This one's 12 minus 1, so that's the case. You're subtracting 12 minus 1 to get to the width. Oh, this one, graph. It's left hand right hand. This time not achieved. That's right, 36, which is 3, 6. You're right, yeah, here's that one. Oh, okay, looks like you guys are on the right track. Part A is 43, part B is 89. Part C is 51 and part D is 83. Yeah, I feel like the most common mistake is with trapezoids, and we have to just remind ourselves that we get down to the trapezoid that we're not subtracting the heights, we're adding the heights, even though the width, we're subtracting the width, right? And then for each trapezoid will only be 2 heights. We're not going to add up all the heights in between, just the ones at the end. So we'll see a bunch of this on the quiz review as well as the quiz. So hoping that these will just be easy points, and looks like you guys are getting it pretty well. All right, go get your phones. Yeah. Check your calendar for your homework.
What days are the help session?
Oh, right. I'm going forward there. Tomorrow morning, Thursday morning, and Friday morning. I'll send out a reminder this afternoon. Yeah.
Okay. They must be able to get it in by the 18th.
Just send it to me, I'll work on it.
Bill, and then one thing is the answer or email.
Okay.